at neutralization point. How is it that you know exactly when neutralization has occurred? So from our background knowledge, we know that neutralization reaction occurs between an acid and a base, right? Specifically an alkali. When these two react, right, the alkali and the acid, at some point, your reactant gets used up to form products. For a neutralization reaction, our products are salt and water. Now, the name of the reaction, right, came about because the products that are formed are actual neutral, meaning that their pH is right about 7. So the reaction brings about compounds that are neither acidic nor basic in nature. Hence, neutralization. But what we're trying to figure out now is how do we determine neutralization point? How do we figure out exactly when that moment is? So there are 3 ways to do this. One, we can use an indicator. So an indicator is a substance that changes color depending on the, what should I say now? The pH value of the substances. So it would be one color in an acid, but a different color in a base. 2, we can use a pH meter. Now the pH meter is pretty much the easiest one out of the 3 to use because you literally have an apparatus that gives you a digital reading. So it is quite easy to know when you have reached 7, pH of 7, because you will get a digital reading on a screen saying pH 7. Then our third way is change in temperature. Now, why is it that they can use a change in temperature? They can use a change in temperature because a neutralization reaction is exothermic, sorry. Now, we briefly mentioned about exothermic reaction when we started looking at acid and bases. When we broke it down, the prefix exo means out, and thermic suggests heat. So pretty much heat is being given out. So when the reaction is proceeding, right, your temperature is going to increase as the reactants do their thing and form your salt and water. So what they can do is to determine the temperature difference between when the reaction started and when the reaction ended. We're going to break them down into different sections. So we're going to take using indicator first, and then we're going to look at change in temperature. So there are several indicators in the lab, but there are 2 indicators that you'll hear about in your reading, right? Or when you're watching the videos, because these are common to use. These are phenolphthalein and methyl orange. All right, as it says here, it's the most commonly used indicators to determine neutralization point. And this is because there's a distinct color change. For phenolphthalein, phenolphthalein is pink in a base, but remains colorless in an acid. So pink in a base, but remains colorless in an acid. Your methyl orange looks more yellow, not so much orange. It looks more yellow, right, in a base, and it changes to red for your acid. So when performing now, how is it that you use the indicator? We use a method called titration. And we started looking at titration, ladies, where you had the use of a pipette and a burette to find a certain volume of either your acid or base that will neutralize a given amount of, so let's say you had 25 cm cube of sodium hydroxide, right? You use the method of titration to find out just how much of the acid would be needed to neutralize 25 cm cube of the base that you were provided with. All right, so during that reaction, your indicator is going to change colors. So we're going to watch a video here now to look at how it is done in the lab. They are using phenolphthalein as their indicator. So we're looking out for a color change of pink to colorless.
Before filling a burette, we should make sure we've placed a small glass funnel in the top. We should also make sure we've got the rest of the equipment we need, including solutions, distilled water, a suitable indicator, in this case phenolphthalein, a 25 milliliter volumetric pipette, 3 clean conical flasks, and a pipette filler. 2 examples of these are shown on the screen. Here we're going to use a more traditional rubber bulb pipette filler, which should be attached carefully to the end of the pipette. Before carrying out the titration, we need to add a few drops of indicator, which in this case is phenolphthalein. It's important not to add more than 2 or 3 drops of indicator, as you don't need it.
All right, so I'm just going to pause it a bit just to highlight what's going on. So in the conical flask, we have our base, and that is why when you add phenolphthalein to it, it looks pink. Now, in your burette is the acid. So what is going to happen is that he's going to add the acid continuously until the pink in the conical flask changes to colorless. That change in color, ladies, from the indicator points out to him that the reaction is now complete. All the reactants have been used up. And so that volume that you're going to record on the burette actually tells you how much is needed for this reaction to take place.
Carry out a rough titration, sometimes called an overshoot titration, to find out roughly how much of our other solution is needed to neutralize the solution in the conical flask. This is done by adding the solution from the burette until we see a permanent color change. We can now work out the volume of solution which we added from the burette by noting the final burette reading and performing a simple subtraction.
Again, ladies, so the first titration that he did, right, is known as a rough titration. So this one is not looking for accuracy, but to give you an idea of how much is actually going to be needed. So he did about 16 centimeter cubes is too much. So he knows that when conducting it again to be more accurate, it is going to be less than the 16 centimeters cubed.
So we're going to add about 14 centimeters cubed by going very quickly from 19 centimeters cubed to 33 centimeters cubed on the burette. Here you can see the solution running in quickly. And once we've added those 14 centimeters cubed, we can adjust the tap on the burette to add the remaining solution very slowly in a dropwise fashion. This should be continued with regular swirling until the colour has been permanently discharged. Now we can work out accurately how much acid has been added by performing a subtraction, and the experiment should then be repeated until concordant results are obtained.
So notice in the first one, ladies, it is just run carelessly until the color changes and you stop it again. So that's a marker to say, okay, it's not going to take more. In his case, it was 16 centimeters. It's not going to take more than 16 centimeters cube for my reaction to be complete, for the end point to be reached, right? So notice in the second run of the titration, when he was approaching 15 centimeters cube, he started slowing down. So at about 14 centimeters cube, he started controlling the tap and allowing only drops of the acid to be placed in the reacting vessel at a time. This is where accuracy comes in now, because you don't want to overshoot at that point, because it means that your solution that you're creating will not be neutral but be acidic. Why acidic? Because you have now passed being neutral, and the excess acid that you're adding builds up in your solution and creates an acidic environment. All right, so that is why you slow down and only add drop wise. So your rough titration gives you an idea of, okay, I don't need more than this. And then the second titration, which is actually the first accurate one, then you start slowing down before you get to that overshoot measurement. And then now you add dropwise until the color changes. I remember they said it must be a permanent change. So there are occasions, when we get back to the classroom, there are occasions when you think the endpoint is there, but then in about 2 or 3 seconds, the color comes back. That is telling you that you're near to the endpoint, but not completely there. All right, so are you getting me so far, ladies?